In this video, we're going to look at one of the most important physical properties of atoms, and that is its mass, otherwise known as the atomic mass. We're also going to be able to work out how to calculate the mass of molecules, known as the molecular mass, and also the mass of ionic compounds, known as the formula mass. When we talk about atomic mass, what we're really talking about is relative atomic mass. And we need to talk about it on a relative scale because we know that the masses of atoms are actually very, very small. For example, the hydrogen atom has a mass of 1.674 by 10 to the minus 27 kilograms. And even the most massive naturally occurring atom, the uranium atom, 3.953 by 10 to the minus 25 kilograms. These are very, very small numbers to use for mass and not very convenient. The kilogram is defined by the International Prototype Kilogram, which is a cylindrical piece of platinum iridium alloy that's kept in a sealed vault just outside of Paris in France. And unfortunately, atomic masses are simply too small for this kilogram mass scale to be used conveniently for us. So what we needed to do was come up with another piece of matter against which the masses of atoms could be measured in a relative sense. And the piece of matter that's been chosen is a carbon-12 isotope of carbon. Now, we know that a carbon-12 isotope has exactly 6 protons, 6 neutrons, and 6 electrons. So its mass can be very precisely defined. What we've done is assigned exactly 12 units of mass to an atom of carbon-12. So we say that one atom of carbon-12 is equivalent to 12 atomic mass units. Atomic mass units are often abbreviated to AMU, or they take on the Greek symbol mu. Now, the mass of a carbon-12 atom, we've said, is 12 atomic mass units. This is an exact number. So for all intents and purposes, the number 12 in terms of 12 atomic mass units has an infinite number of significant figures. The actual mass in kilograms of a carbon-12 atom, 1.99 by 10 to the minus 26 kilograms. And if we divide that number by 12, we can see that one atomic mass unit is equivalent to 1.66 by 10 to the minus 27 kilograms. That's worth knowing from an academic point of view, but in practice we'll rarely ever use that relationship. What we will actually use is the knowledge that a carbon-12 isotope has a mass of 12 atomic mass units, and that, relatively speaking, every other element in the periodic table has a mass that has been measured as being relative to the mass of 12 atomic mass units. And what we can see is that these numbers under the chemical symbols in the periodic table now start taking on some meaning. The number under the number under the element in the periodic table is referred to as the atomic mass, and as we've seen, we've just given it some units, the atomic mass units. In reality, however, it should really be called the relative atomic mass, because that mass is actually relative to the mass of a carbon-12 atom, which we've assigned exactly 12 units of mass, or 12 atomic mass units to. So we can look at the periodic table and pick any element in the periodic table, for example, hydrogen, number 1. We can look at the number underneath the symbol, 1.00794, and we can say that the atomic mass of hydrogen is 1.00794 atomic mass units. So roughly speaking, a hydrogen atom is 1/12 as massive as a carbon-12 atom. We can look at another element, magnesium for example, and we can see that its atomic mass is 24.3050 atomic mass units. And roughly speaking, a magnesium atom is twice as massive as the 12 atomic mass units for a carbon-12 atom. We can look at number 6 on the periodic table, carbon. Now, carbon's an interesting one because its atomic mass, 12.0107 atomic mass units. It's not exactly 12. The atomic mass of 12 is the atomic mass for a carbon-12 isotope, but carbon samples actually have carbon-13 isotopes. 1% of them are carbon-13, and carbon-14, 0.1% are carbon-14. So the average mass of the average carbon atom is slightly above that of carbon-12. And so this is why we get 12.0107 instead of exactly 12, because what these numbers are actually representing all over the periodic table is the average mass of all the available isotopes when their relative abundances are taken into account. So we can actually work out the mass of molecules as well. It's known as the molecular mass. And what we do is we simply sum up all of the atomic masses of all the atoms in that molecule. And for example, we can use the molecular compound water as an example, H2O. Now we recognize that H2O has 2 hydrogen atoms associated with it. We can look up hydrogen in the periodic table, number 1, and we see again that its atomic mass 1.00794. So the contribution from those 2 hydrogen atoms, 2 times 1.00794. We can see that water has 1 oxygen atom. We look up oxygen on the periodic table, 15.9994 atomic mass units, and the contribution from oxygen to the overall molecular mass of water being the 1 times 15.994 atomic mass units. We can sum these up, 2 times the mass of hydrogen plus 1 times the mass of oxygen, and we get 18.015 atomic mass units. So the molecular mass for any molecular compound can be calculated in exactly the same way, simply adding up all of the atomic masses of all of the atoms in the molecular formula. For ionic compounds, it's slightly different. There are no molecules, and so what we actually refer to is a formula mass. But again, we simply add up all of the atomic masses of all of the atoms in the formula unit. So an ionic compound such as calcium phosphate here, we can see has 3 calcium atoms. We look up calcium on the periodic table. There it is there, number 20. We see that its atomic mass, or relative atomic mass, 40.078 atomic mass units. So the contribution from those 3 calcium atoms, we multiply that atomic mass by 3. We can see that there's a single phosphorus atom inside the brackets here, but we also recognize that there's a subscript 2 outside the bracket. So in total, we've got 2 phosphorus atoms there. We can look up phosphorus on the periodic table, number 15, see that its atomic mass is 30.9738, and 2 times that number there is the contribution from phosphorus to the overall formula mass of calcium phosphate. We can see that inside the bracket, oxygen has 4 atoms, but the 2 outside the bracket means that we've got a total of 8 oxygen atoms in this chemical formula. And we look up oxygen in the periodic table, number 8, and we see that its atomic mass 15.9994, the contribution from oxygen being 8 times that number. We can sum all these up, 3 times the atomic mass of calcium plus 2 times the atomic mass of phosphorus plus 8 times the atomic mass of oxygen, and we get the number 310.177 atomic mass units. And again, the formula mass for any ionic compound can be calculated in the same way, simply by summing up all of the atomic masses of all the atoms in the formula unit. So atomic mass, molecular mass, formula mass. The number under the chemical symbol in the periodic table now has a new and significant meaning for us.